Hello everyone. In this video we are going to talk about basic statistics, and for that reason not only I need NumPy, since I want to do a plot of a histogram I need matplotlib, and then I need two methods of skewness and kurtosis from the scipy.stat. So the first thing I do, I'm going to go ahead and generate a sample with 1,000 data points drawn from a normal distribution, a random set of data from a normal distribution using np.random.normal, which we discussed earlier, with an average of 0 and a standard deviation of 0.1, and call it Sn, whatever you want to call it. And then I'm going to look at basic statistics of that, including the average, the standard deviation, the median, the interquartile range, the skewness, and kurtosis, which are basic statistical measures, right? So let's go ahead and look at these, and then I'll explain as we go through the numbers. So let's go ahead and run it. And you can see that the average of the data should be 0. It's very close to 0. It's not perfectly 0 because this is just a sample of 1,000 numbers, not a population with infinitely many numbers. So it's close to this mu, but not perfect. The more data we draw, the closer this guy is going to be to 0. So that's your mean. Standard deviation here, as you can see, is very close to 0.1. And it should be, that's an estimate of that. Then we have median of the data, or the middle point, which for a normal distribution should be the same as the average. And you see this number is actually close to this one and close to 0. That's the sorted data, the median. Then we have the interquartile range, which is the quantile 75 minus quantile 25. And we can use this for the outlier detection and outlier analysis using the box method. I'll show you after we go through these numbers. I'll show you how to use it. And then we have the skewness and kurtosis. And skewness, as you know, is a measure of deviation of the center of the data to the left or to the right, toward the smaller or toward the higher data. For a normal distribution, the number should be 0. And you see this number is basically close to 0. And then we have kurtosis, which is the measure of peakedness of the data. So whether the data peak is flat or very sharp. Again, for a normal distribution, if you basically subtract the 3 from the fourth central moment, then you can get kurtosis. And if the code is written as such, then this number should also be close to 0 for a normal distribution, which you can see it is. And as I said, the more data you have, the better these numbers are going to be, the more accurate. So instead of 1,000, let me go and use 100,000 and see what happens, right? Now, of course, it takes a little bit more time, but we should be able to get better numbers. So now if you look at the average, instead of 2 decimals and a 2, now you have 3 decimals and a 3. So it is like probably like 6 times or so smaller now, the average, closer to 0. You see now this was 1 and 2 zeros. Now this is 1 and 3 zeros. So it's much closer to this one now. And if you look now, you see the median is also closer to 0. The skewness is closer to 0. The kurtosis is a little bit smaller, closer to 0. And the interquartile range is close to the previous number, a little bit more accurate. So the more numbers we have in the sample, these estimates are closer to the actual population parameters. Now, as I said, you can use this interquartile range, and you can get what? You can basically get to have an outlier analysis. So for example, let's say you want to do outlier analysis, right? So what you can do is you can pass your vector to a data, and you can pass a sample data, and then that function, let's say that does the outlier analysis, can tell you whether the data is an outlier or not. So let's go ahead and add that for practice, right? So say def, and then is outlier, right? And then you pass to it some data, and you pass to it a sample, right? And then this guy is going to do what? it is going to get the interquarter range of the data, right? Let's go ahead and do that. So this, I call it IQR, right? The interquarter range of the data. So instead of SN, I would call it data. And then if you add 1.5 times what? The interquarter range to the 25 percentile and to the 75 percentile of the data, subtract 1.5 from this, add 1.5 interquarter to this number. Those are the limits. So here I can say upper limit is equal to what? Is equal to this 75% plus 1.5 times IQR. And then the lower limit for an outlier is the 25 percentile minus 1.5 times IQR. So now if your number is between these two, your number is not an outlier, otherwise it is. So here we can say if what? If your sample is bigger than or equal the lower limit and the sample is less than or equal the upper limit, then you print that the given sample is not an outlier. And then \n, and then else, and then if that's not the case, you print that it is an outlier. Okay? And that's it. So now that I have my outlier, or I call it is outlier box method. If this is gonna work, then that is a good practice for me. So let's go ahead and try it out now. So here we create a sample, and for sample, let's get it, let's give it some number. So here your number is, the average is 0, standard deviation is 1.1. So you know the spread of the normal distribution is almost 3 plus minus 3 standard deviation added and subtracted from the mu. So it's literally between negative 0.3 and 0.3. Okay, so here I'm going to use a number sample and set it equal to 0.5, and then go ahead and call this function and pass to it the SN data that we have already in that sample. And the next time we're going to generate some data which is inside, so let's say 0.25 this time, or 0.2, and call it again and see what happens, right? And let's go ahead and run this. Hopefully no error. There we go. You see? When we gave it 0.5, it says it is an outlier. When we gave it 0.2, it is not an outlier. And you see it is working just perfectly fine. So here, this is called what? Box method outlier analysis. So I added this for you as a bonus so you learn about the statistics. The other important statistical tool that you always use and you want to learn about are histograms, which show basically you break the whole range of data into bins, and then for so many bins, for each bin, you count your data and throw them inside one of the bins and show on an axis the number of data per bin, which we call frequency. So you plot frequency versus bins, and that is an approximation of the probability distribution function PDF of the data. So what I have here is I pass my data that I just generated, I pass it to, and let me go back to 1,000 data points, and I pass it to the histogram method and say, hey, histogram, I give you this data and use 30 bins and density true. I'll tell you what this one is. So go ahead and give me the bins. Where are the bins? Which are determined from the number of bins and the minimum and maximum of the data, the centers of the bins, and then count comes from counting really from the histogram method. And then you have a third output, which is called what? Which is called ignored. And here, as always, if you don't know something about a method, you can always go and look it up in matplotlib, right? In this case, it's the histogram. So you see the histogram needs the data, needs the number of bins, needs the range if there is, which we don't need to. It is determined by max minus min of the data. You can have the density to be false or true. I'll tell you exactly what this one is. So you can provide a lot of data, and then the returns for this is X, right? The bins, sorry, let me go to here, the returns. Basically, the bins, right? The counts, the bins, and then this is called the patches, which is basically we don't need it, and this is for when you have multiple inputs of data and we don't have that. And so if that's why here you say ignored, which basically means I really do not need to have that output. And the reason we do it is so the outputs for numbers and for bins are exactly allocated to these guys, and not one of those patches or something is stored in them. So we get 3 outputs, but we ignore this guy. And that is interesting, huh? Call this ignore, means I don't care about it. Now, what does this command hist do? So it gives us all of this data, but does it give us a plot too? Well, we can check that. Let's turn this command off, which is basically for creating this plot, the red plot of the histogram, the overlay. So if I go ahead and turn this one off and create my plot, let's see what I get here. You see, so the histogram does give you a histogram plot, which is a bar plot here, right? It does give me a bar plot, absolutely. So now on the top of this, I want to draw a perfect histogram of normal data. Which normal data? A normal data with the same mu and sigma that I used for this Sn with these numbers. I want to overlay it on this so you see that this discrete histogram is a good approximation of that continuous curve, which we call what? We call it the probability distribution function, the PDF. So for that reason, I'm going to go ahead and add this next command, which is plotting that red curve for me. So you see, I'm asking it to plot a red curve on the top of that with a line width of 2. And what is the data that I'm creating? The X is bins, and the Y uses the bins. Subtract, and bins here are the center data for the bin. These are just a number, not a range. That's the center of each bin. You subtract them from mu, square them with a negative sign divided by 2 sigma squared, do an exponential function on that, then divided by sigma times square root of 2 pi. And this is exactly the formula for what? This portion. This is the formula for a normal distribution, right? Where instead of X, instead of your variable, bins is going to be replaced, but you are using the same mu and you're using the same sigma, and overlaid on the top of that in a red color, and then add the X, Y label, and then show the plot. So here you expect that you get an extra curve on the top of that histogram. And here we go. You see? So as you can see, this discrete histogram is a relatively good approximation of the ideal PDF. And if I use more bins and if I use more data, clearly this guy, this blue one, should be much closer to what? To the red one. And for that reason, I'm going to change the number of my bins. So this time I make it 100 bins. And I make this guy a lot more data, 100,000 data. So of course it takes a little bit more computation, but ideally I should get a better result this time. So let's take a look and see. Here we go. You see, now I have more bins, I have more data, and you see the blue curve is very, very good approximation of the blue histogram of the red curve. The last part we're going to talk about is this density true that I mentioned. So what happens if I make this false or I remove this portion? What happens? Well, remember that our red curve and the histogram were matching very well. Now, if, as I said, make this false or remove this portion, just cut it out, look what happens. They don't match anymore. Look. And I use a smaller data this time again. You see now, this curve, which is an ideal PDF, and that histogram, they do not match. I mean, the scaling is different. For an ideal PDF, the area under the curve is 1, but for this histogram is not. And if you look at the frequencies, they are going high up to 70 something and so on. And the area under the curve is not 1. So when we say make that density true, which means you have to divide these counts by a fixed number so that the maximum count that you have is not equal to 70 something, it's equal to what? Is equal to that 1 over sigma square root 2 pi or something close to that. So you have to do some normalization here and scale it down so the area under the curve of this whole thing becomes basically similar to that guy, becomes 1, right? Otherwise, as I said, this histogram does not represent a true probability distribution function, but the red one does. So when you say true, it means, hey, do that normalization, make sure the area under the curve is 1, and that way you can assure that those two can be laid over each other and they can be compared. So if you want to compare an ideal PDF with a histogram, you have to use density true. But if you just want to see really how many counts, because these counts are not real. You don't have 1, 2, 3, 4 counts in these bins, right? Because remember, your total sample is 1,000 data. If your frequencies are 1, 2, 3, 4, sum of all these heights is not going to be even 100. Okay, so when you say density is false or don't do it, that's where you want to look at the actual number of data in each bin. And you just want to look at histogram alone. But if you want to compare against a real PDF, that's where you have to say what? Density is what? True, so you can do the comparison. So hopefully this video was useful to you, and I will see you in my next lecture. Thank you.